GPT can have up to 128 partitions. It can also store a huge amount of data, and so it can manage. Now these are devices that it can manage. That I think that might be big enough for me for next week. That might just do it. Hi, I'm DJ Werq. On this episode of the Cyber Gizmo, I'm going to be talking today about block devices, or more importantly, storage devices, and how does Linux actually manage those. So, yeah, I'm bringing back the Linux internals class again. This time I'm going to be forwarding on to the next stage of this, which is the Linux storage mechanism and how Linux manages storage. So as far as Linux is concerned, what are we going to need to cover in order to talk about that? So we need to talk about block storage. We need to talk a little bit about what disk partitions are, and then we need to talk about the types of partitions, and those are the MBR and GPT. We're also going to be talking about how to format those disk partitions, and then how does Linux manage them once all that's done? And then finally, how do I mount them onto my file system? How do I get those block devices mounted so I can use them? And then we'll talk about some specialty cases, and that would be RAID and LVM. There's a lot of different types of block devices, like this one, rotational devices. A block storage is the same thing as a block device. So a block device is a piece of hardware to Linux, and that device is used to store and retrieve data at I'm going to say relative high speed because it's never fast enough. Linux calls these block devices because it reads and writes to them in a fixed size chunk or blocks of data. So yeah, it wants to pull a fixed size. Block devices can be mounted anywhere on the Linux file system tree. And if you don't know what the Linux tree is, just go out to root, just type in tree and you'll see it. It'll go all the way down. You'll see it. Disk partitions are basically segments out of that storage on that device. So you can basically carve it up. You can create additional partitions out of that storage so that you can use them for different purposes. So for example, you might use one partition to hold the boot directory. So if you're building up a new distribution and you want to be able to, you'll have a different partition for your boot. You may have another partition for root, and then another partition maybe for your swap. Or you might have one for your home directory, or you might, have one for var or temp. But yeah, you can divvy up your partitions any way you want. And the two structures that are most commonly used today, although MBR isn't commonly used too much, at least not by me, but I mean, I'm sure there's some people that still use it, but the master boot record is the oldest of the two, and that can hold 4 primary partitions, and it can manage drives up to 2 terabytes in size, which is the reason why you don't see MBR too much anymore. So can you add additional partitions once you filled up the 4? Yeah. You can do the first 3 and then turn the 4th one into a special type of partition called an extent, and then you can add additional logical partitions to that. So yeah, but then you've got another structure the drive has to go through, so it's not really optimal. So GPT, which is a acronym inside of an acronym, is actually the GUID partition table. And GUID stands for Globally Unique Identifier. So to put this all together, GPT is the Globally Unique Identifier Partition Table. I don't know who comes up with these, but man, she could have come up with something easier than that. So GPT can have up to 128 partitions. It can also store a huge amount of data. And so it can manage, now these are devices that it can manage. I think that might be big enough for me for next week. That might just do it. It might just do it. That's 9.4 billion terabytes. Yeah, that should do it. GPT, of course, is preferred today. Formatting the block devices, and what does that do? So first of all, you have to prepare the partition to hold data. So there's structures that have to get written down onto the drive in order to make it ready to be able to receive and store, and then be able to read the data back and then send it on request. So file systems that you can use, generally you have to have a file system that you need to identify. So when you're getting ready to format a block device, you first have to think about what file system you want to put on it, and on that particular partition. So yeah, there's a bunch of them. I'm not going to cover all of them. These are ones that I'm just going to talk about for Linux. Yeah, there's FAT32 and there's NTFS, and yeah, there's ext4 is probably the most common, and that is the extended file system version 4. That one you'll probably find more commonly in most of the big name Linux boxes, with the exception of Fedora and Red Hat, because they don't use ext4. But a lot of them other ones do. The Linux operating system it's well suited to handling Linux operating system workloads, and also the types of read and writes that C applications do on Linux as well. So I mean, yeah, it's pretty ubiquitous for that. XFS originated from Silicon Graphics workstations, and that is a high performance file system, and a lot of its performance comes from the fact that it does do journaling, but it only does metadata journaling. It doesn't do data journaling like ext4 does. So yeah, it's a high performance file system, but it comes at a cost. So it is the default file system that's used on Red Hat Enterprise Linux, and in fact, there's also one problem. So XFS, because it doesn't journal data, the file system can become corrupted if there's an abrupt power loss. So just be aware of that. They do take a little bit more care. It's a little bit more fragile. So ButterFS is a modern feature-rich copy-on-write file system. Its architecture allows for some fancy footwork, so that it allows it to do snapshots and cloning. You can create volumes on it. So you don't have to, in a traditional file system, you have to create a partition, and then you have to format it, and then you have to mount it. This on ButterFS, you can create volumes on the fly and just mount them. So once I've created my base, I can just, it's like ZFS, where you can basically just create all these volumes and then use them. So like ButterFS still has a few known problems, particularly when it gets full, and then there's some debate about its suitability for production workloads. But nonetheless, it has become the de facto file system for both Fedora and SUSE. I think it's just OpenSUSE, because I think SUSE itself is using XFS. So yeah, the enterprise version of SUSE, I believe, uses XFS. Correct me if I'm wrong. It's been years since I've used the enterprise version of SUSE, but I don't think they changed. But I do know that the default on OpenSUSE is ButterFS. You also have ZFS, and that is a copy-on-write file system that supports snapshotting, cloning. You can organize volumes into RAID-like arrays. Ubuntu now ships a kernel and a distro which allows the installation of a ZFS pool on your root file system. Debian includes the source code for ZFS, even though the ZFS has somewhat of a controversial open source license, which is incompatible with the Linux kernel. The next question is, how does Linux manage block devices anyway? So in Linux, just like Unix, everything is a file. So block devices, they create entry. The kernel takes the block device and creates an entry in the /dev directory for not only each device, but each partition on that device gets a unique name. So, for example, you might have a drive that's mounted as /dev SDA. So that'd be your drive name, would be SDA. Your first partition would be SDA1. Second partition that's on there would be SDA2, and so forth. So Linux will create Linux. The kernel has its own map of devices, but if you ever look at them, you're like, where did they come up with that? It's like they don't even make any sense. And then they map it to one of these devices based on a set of rules. And there's some other applications that get involved, and we'll talk about those next time. But for now, just the Linux kernel, just think of it this way. The Linux kernel does it, and don't worry about it. It just creates it. So, but it's a symbolic link that points back to the original hardware device that the Linux kernel is managing. That way it knows what actual physical device to talk to. So, and how else does the Linux manage the block devices? Well, there's a couple of other directories that are in your dev. One of them is /dev disk. And in there, you'll find a whole bunch of other directories, and you might see this one by part label. By part label is a partition label that you can define when you create the partitions on GPT. And then you'll find a mapping by that name. And that mapping can be used to mount the drive. So, yeah, you can manage the drive with that name. There's also part UUID, which is a unique identifier, a universally unique identifier for partitions, and again, that is also GPT. There's a dev disk by label, and those are defined labels for disks or partitions. So again, similar to the part label, the label is at the drive level, but it can also be used for partitions too. So other links are by label, so I think that's a repeat. And then by UUID. So UUID, you can assign a unique identifier, and each partition will carry that. So you can then use that to mount the file system as well. Generally, it is recommended that you use one of these mechanisms, whether it be by UUID or by ID. That's using the serial number off of the hardware. Sometimes that one, by ID, is really good, especially if you have a lot of drives and you're trying to find the one that failed. If you have the serial number there, you can pull the drive out, shut it down, pull the drive out, and look at the serial number and see if that's the one that matches the one that failed. Or if you're one of those really organized shops that has your drives labeled in a book or on a card that tells what serial numbers are in which slot, that's really helpful too. So anyway, dev disk by path. And those are they're links that are constructed by the system that interprets the hardware used to access the device. But by label and by ID are usually the most common ones that are used. Although UUID you'll find is probably more commonly used by most distros when you're building up from a live CD. So, and those are fine. They work just fine. The dev file is used to communicate with the kernel. But there's a lot more to the story of that. So to mount a file system, you have to pick or create a place on the file system tree to place it. So, well, whatever you do, I would recommend not using ones that are already on the tree. The FS tab is a file that is normally used to define the mount point, the device name, the mount point, the file system, and then some mounting options. There's some other goodies in there too. And then that, at boot time, it follows the order of that file to mount the file systems in. It starts at the top and works its way down. You can use a different file if you want to, but you got to go in and define it to system demount. That's uncommon. It's very uncommon. RAID. So there's some complex storage management you can do. Now, I'm not going to cover all of these. I'm just telling you about them, that they're here. So yeah, there is RAID that you can build inside of Linux. It is normally a software RAID, but there are hardware devices that you can add to Linux that will actually do real RAID. So yeah, you have RAID 0, which is striping. RAID 1 is mirroring. RAID 5, which is single parity RAID. That means one drive can fail, and you can still reconstruct the RAID. RAID 6 is double parity. That means that two drives can fail. You can still construct the RAID. RAID 10 is a combination of RAID 1 and 0. So it gives you the benefit of performance of RAID 0 without the disadvantage of, if you lose a single drive in RAID 0, you're done. Your RAID is toast. It is destroyed, and you will have to build it from backup. So mirroring gives you a single device as your redundancy, but it comes at a cost of half of your available storage is used to construct the mirror. So yeah, I'm not going to explain all that again here. I've got some videos on it. I'll put some links if you're interested in going through it even more deeper than this. So the other one is LVM, Logical Volume Management, which is, believe it or not, Ubuntu on the workstation, if you install it default, you'll get an LVM. If you don't pick ZFS, you'll get an LVM. They will build it out for you. The idea behind LVM is that there's some things that a regular file system just simply cannot do. And so LVM is around to address that. It's meant to provide capabilities like being able to expand or take snapshots of the directory, and that you can make some pretty complex file systems. For example, you can take a whole bunch of disks and then you can combine them, and you can have the storage pool store data across all of them. So you can just take a JBOD basically, and adjust a bunch of disks, JBOD. So you can just take that and just create a whole bunch of disks and then store it across all those, and you can create an LVM to manage it. You can also increase the amount of storage. So I can, say I'm running out of disk in the LVM pool, I can just throw another drive in it and mount it up, add it to the pool, and all of a sudden that drive is now providing space to the pool. So yeah, you can create file systems that span multiple disks. You can expand. You can take snapshots. You can even move physical disks to a different logical volume if you need to do that. So yeah, those are just some things that a physical file system just can't do. So what did we talk about? So the first thing we talked about was what is block storage to Linux? What is a block device? Then we talked a little bit about partitions and what they're used for. We also talked about MBR, the master boot record, versus the GUID partition table. So formatting, we also talked about formatting disk partitions, and then we talked a little bit about how Linux manages those partitions. We also talked about how to mount those block devices, and then we got into RAID and LVM a little bit, and talked a little bit about some of the craziness you can do. Now, like I said, I kind of avoid all that because yeah, that has a tendency to make you the belly button to push, so as we used to say. You don't want to be that guy. Let me tell you, it's not fun. Anyway, so I hope you enjoyed this video today. Please like and subscribe if you do, and leave a comment below and let me know what else in the Linux internals you're interested in. Hope to see you again soon. Bye for now.